Hello everyone. In this session, we are going to discuss some fundamentals of MOSFET amplifiers. Similarly to BJT, we can also use MOSFET to make a small signal amplifier. Here is an example of a conceptual MOSFET amplifier. I say it's a conceptual because in the real situation, we usually will not bias transistor in this format. With this conceptual MOSFET amplifier, and we can obtain a voltage transfer curve. In this voltage transfer curve, the horizontal axis is VGS, which is the voltage applied to the gate, and the vertical axis is the VDS, which is the voltage at the drain. When we have a very small gate voltage, and because the gate voltage is small, when it is smaller than the threshold voltage, there's no channel induced. If there's no channel induced, then there's no current through the drain resistor ID here. No, because there's no current, which means there's no voltage drop. And what we get, the voltage at the drain will equal the voltage supply. So VDS will equals VDD. If we continue increase our VGS above the threshold voltage, then we are going to go into the saturation region. So in the saturation region, we are going to see a drain current. Now once we have a current, and the current will cause the voltage drop across the RD here. And this voltage drop will reduce our drain voltage. And from this curve, we can see the voltage at the drain was slightly reduced when we increase our gate voltage. If we continue increase our gate voltage, at that point when VDS equals VGS minus VT, and here we get to the boundary between saturation and triode. If we further increase our VGS, and we are going to go into the triode region. And in this triode region, and we are going to see a larger current, and most voltage will be dropped across this drain resistor, and we are going to see a small voltage at the drain here. If we are able to make the transistor working at a certain point, for example, a Q point in this curve. Now, if the Q is located in the segment of A between A and B here, and then we can make an amplifier. If we input our signal at the gate with a small variation, and then at the drain, we are going to get a larger variation of the signal. The slope at this Q point will give us the voltage gain of this small signal amplifier. As we can see, this Q point is critical. Right? For the analysis of the DC operating point, we can set our small signal input VGS equals 0, and then we can determine the drain current in saturation mode. Now this is the drain current in saturation mode. If we apply a KVL, and we can have this equation here. If we rewrite this equation, we get the load line. Load line is the drain current equals the voltage drop across this drain resistor and divided by the drain resistor value, and that gives us a current. Now this current is a straight line. If we know the gate voltage, and we can locate where is our working point, our quiescent point, Q here. In order to make the transistor operate in the saturation region, we need this condition here. So this VDS must be larger than or equal to VGS minus VT, or equivalently, VGD is less than or equal to VT. Similarly to what we have observed in the BJT amplifier, we need to make sure the above condition must be satisfied for the entire signal swing. So that means the Q point has to be somewhere in the middle, which will provide some symmetric maximum swing on the signal. this figure shows two working points. Neither of them are good choice. For Q1, and we are going to experience a signal cut on the right hand side. And on the Q2, we are going to experience a signal cut on the left hand side. With a small AC voltage signal applied at the gate, so the total voltage will equal DC voltage plus the AC voltage. If we plug in this to the saturation current equation, and we can rewrite the whole thing, and we will obtain three terms here. So the first term, we call it the DC components, and the second term is the linear AC components. Now the third term here, which is the last term in the equation, is a nonlinear term, which is undesirable for a linear amplifier. So for linear operation, we will require this last term to be small enough that can be ignored. And when this last term is much smaller than the second linear term, or when the VGS is much less than 2 times the overdrive voltage, and we can ignore the last nonlinear term. We only reserve the linear term in the equation. By ignoring the nonlinear term, now the total drain current now is approximately the linear summation, which is equal to the DC term plus the AC term. And remember, our DC current can be calculated by this formula here, and our AC current will be the second term, can be calculated by this formula here. So now the AC current is modulated by the small AC voltage signal applied at the gate VGS here. The AC current now is linear changing with respect to VGS. From the above expression, we see that the AC drain current is related to VGS by the so-called transconductance GM. If we define the GM equals Kn prime and W divided by L times VGS minus VT. Remember, VGS minus VT equals VOV, which is the overdrive voltage, and we can express our transconductance GM by this formula here. Apparently, GM depends on the biasing condition, similarly to what we have observed in BJTs. And physically, this transconductance GM equals to the slope of ID versus VGS curve here. It is the slope at the Q point. Apparently, when we changing our Q point, and we are going to get a different transconductance. Now that's why we say GM depends on the bias. For this conceptual MOSFET amplifier, the slope at Q will give us the voltage gain, which can be calculated by taking the slope at this point. And we can also easily obtain the amplification gain. And if we assume this line is linear and VGS minus VDS will equals negative IDS times RD, because we have a negative sign because this phase of the signal actually is inverted, and then our voltage gain equals negative GM times RD. And we are going to give a further analysis on this formula in future slides. Noting the DC drain current, which is the saturation current, and we can rewrite this to this formula here. And that means the second part actually is our GM, which means we can express our GM by RD over GS minus VT divided by 2, that is VOV divided by 2. Now recall the GM of BJTs. The GM of BJT equals RC divided by VT. Now for MOSFET, GM equals RD divided by VOV divided by 2. So we can see there's a big difference here because VT is a very small number Vt is the thermal voltage. That is only 25 millivolts. But VOV divided by 2 is going to be much larger, typically much larger than 0.1 volts. So therefore, for the same bias current, the MOSFET GM is going to be much smaller than that of a BJTs. So that's one thing you need to keep in mind in the future for designing MOSFET based amplifier. So the GM is smaller for MOSFET. In order to analyze the circuits, we usually will use equivalent model to replace the transistor. And here we can use a small signal pair model to model the transistor. And the transistor node can be considered as a voltage controlled and current source. So the voltage applied at the gate will control the drain current. Remember, here there's no current into the gate. If we consider the early effect, and then we needed to include output resistance RO here. And this output resistance needed to be in parallel with this current source. Another model to model the MOSFET is a small signal T model. In the small signal T model, we needed to explicitly specify the boundary condition. So that is Rg equals 0. So there's no current into this point. And if we needed to consider the early effect, we also needed to include the output resistance RO here. And this output resistance RO will be in parallel with both the current source and also the source resistance. And this is a similar model as a current controlled current source. Now let's discuss a few examples for the MOSFET based amplifier. In this example here, we are going to determine our voltage gain here, AV, and also need to calculate the input impedance and output impedance by giving the condition Vt equals 1.5, Kn prime, W over L equals 0.25 milliamps per volt square, and Va equals 50 volts. Now let's take a look at the DC voltage on this amplifier. This figure shows the DC analysis. From this DC analysis, we can tell the drain and the gate actually is connected by this large Rg here. However, there's no current into the gate, which means no current through this Rg. So that means the gate and the drain will have the same voltage. I think in a previous session, we already analyzed, and this situation, the transistor should work in saturation mode. The reason is because this gate and the drain has same voltage. Now this VGD equals 0. It should be less than Vt here, the threshold voltage. Once we verify the transistor is working in the saturation mode, and we can use the saturation equation to calculate the drain current. In order to determine our gain and input impedance and output impedance, we needed to do the small signal analysis. First, to replace the transistor by the small signal model. Here we are using the pair model. And in small signal analysis, all the DC supply will become ground. And here we ground our ID here. Now Rg here is external, is not part of a transistor model. It is an external device. It connected between the gate and the drain. And we have this Rg here. And this will give us the total small signal model. And we have these three resistors here, Ro, Rd, and Rl. Now this can be combined into a single one, that is Rl prime. Now, from this further simplified model, we can calculate our output voltage. The output voltage now will be equal the current through this resistor and times the resistance. Now the current is the current difference between these two. This II which is the current through this RG here, and minus the drain current GM-VGS will give us and this current through this resistor, and that will give us the voltage output. Now the current into or through this RG here can be calculated by the voltage difference. Now here is VGS and minus VO divided by RG. And if we rewrite, and we have this formula. Remember, VG divided by VGS actually is our gain of the amplifier. So we can replace this by our gain and we get this formula. To calculate our input and the resistance, and we can directly using Ohm's law. We have a voltage input VI and divided by the current. And the voltage here actually is equal VGS. Right? VI equals VGS. And II, we can just plug in II we obtain in this formula here. We will get our input impedance RG equals 1 minus AV. Now with these two equations we obtained from the previous slide, and we will be able to figure out how much is our voltage gain here. Now VO here, and we can replace II by the formula here we obtain. Then we have this formula here. For this formula, if we divide VGS on both sides, then we will cancel all the VGS on the right hand side. On the left hand side, it becomes VO divided by VGS. Now VO divided by VGS actually is our AV here. Now looking at this formula, and if we rewrite, we will obtain our amplifier gain AV will equals here. Now because RG is a bigger value, and this is going to be very small, and this is also going to be very small. And if we ignore them, the AV will be simplified to negative GM times IL prime. To calculate our I out actually is pretty straightforward, and by looking into the circuits using a Thevenin equivalent analysis. For Thevenin equivalent analysis, this RG actually needed to goes to ground, and then the output resistance will equals RG and RO and RD, and these three in parallel. Now let's take a look at another example for the similar concept amplifier. Now the VDD equals 5 volts, RD equals 10 kilo ohm, and VT equals 1 volt, Kn prime equals 20 microamps per volt square. W over L ratio is 20, and VGS is 2 volts, and lambda equals 0, which means we are going to ignore the early effect. We were asked to find the DC current ID and the DC voltage VDS. Also to find the transconductance GM, and to find the voltage gain AV. If we input an AC signal VGS equals 0.2 sine omega t, and find the maximum and the minimum variation of VD here, and also determine the second harmonic distortion. Remember, in our simplified model, we ignored the harmonic part, and if we consider that, we are going to see how much distortion it can generate. Now first, to determine the drain current and the drain voltage. And we see from the circuits, VGS is larger than VT, right? Because VGS equals 2 volts and VT equals 1 volt. So which means we are going to induce a channel in the transistor. So the transistor will either work in the saturation mode or in the triode mode. Now let's first assume it works in the saturation mode, and then we can verify whether it is saturation mode after we do certain calculation. Now, if the transistor works in the saturation mode, we can use the saturation equation to do the calculation and then obtain the drain current equals 0.2 milliamps. Now once I have the drain current, and then we will be able to calculate the drain voltage, which is the voltage supply minus the voltage drop across the drain resistor. That will give us a 3 volts. Now with the 3 volts at the drain, now let's check whether the transistor is working in the saturation mode or not. Now the gate voltage is equals 2 volts. Now VGD now equals 2 minus 3, that is negative 1. It must less than VT, right? So this is the condition actually for saturation mode. So the transistor now is indeed working in saturation mode. It is easy to determine the GM, the transconductance GM. Just plug in the value to the formula and we can obtain the transconductance equals 4 millisiems. So determine the voltage gain, we needed to first construct the small signal equivalent circuits. And here is the small signal equivalent circuits. From these circuits, and we can immediately get our output signal, right? That is negative GM times VGS times RD. That is because the current into this RD and equals the drain current. Here is the drain current. And we have a negative sign because the current goes this way in the resistor. So we get our voltage gain here will equals VO divided by VGS. That will give us negative GMRD here. Plug in the value and we get our gain equals negative 4. Now let's take a look at how much is our AC VD and also the total VD. Now the AC VD can be calculated by the gain equation here or gain definition here, right? So the AC VD will equals AV times the AC VGS. So that is negative 4 times 0.2 sine omega t will give us negative 0.8 sine omega t. Now look at the total VD here. Now the total VD is the DC components plus the AC components. So the AC components will have a variation from negative 0.8 to positive 0.8. When the ACED goes to the positive 0.8, and we have this one, so this VD is the DC value is 3 plus positive 0.8. That gives us 3.8 volts. Now once the AC VD goes to negative 0.8, and we have a VD minus VD, and equals 3 minus 0.8 equals 2.2 volts. So as we can see, the voltage, the total voltage at the drain will change from 2.2 volts to 3.8 volts. Now in the end, let's determine the second harmonic distortion. Now to determine the second harmonic distortion, we first need to recall that the total current we obtain without ignoring the harmonic term here. If we plug in all those values, the DC part and the AC part, the high order part, and we are going to get the total DC current in this formula. That is 200 and plus 80 and plus 8 times sine square omega t. Now that's 200 actually is our DC current. 80 sine omega t is our linear AC current. And the last term is contains our harmonic distortion. Now using the trial geometry identity, and we can rewrite this sine square omega t equals 1/2 minus 1/2 times cosine 2 omega t. Now this last expression in our previous slide will become this way, right? If we rewrite, then we get this formula here. As we can see, the DC current actually shifts upward by 4 microamps. Now the AC components doesn't change. And the last term here actually is the one gives us the distortion. But its frequency is twice the frequency of the input signal. The second term, 80, is our linear components, and this is our nonlinear components. So the ratio will give us the distortion rate. So the second harmonic distortion rate can be calculated, and which is 5%. Until now, we discussed the fundamentals of MOSFET based amplifier. So in next session, we are going to discuss MOSFET amplifier biasing and also the configurations. See you next time.